Good afternoon. Welcome to our special condensed matter seminar today. The topic will be on the element and also metallization of hydrogen. And hydrogen, right, is the simplest atom. And all of us know this element very, very well. When we're young, we have hydrogen balloon or helium balloon. And when we study quantum mechanics, hydrogen atom is the first application of quantum mechanics. And metallic hydrogen, right, was predicted, I think, 6 decades ago. And scientists have been working on the realization of this solid for the last 60 years. And there are some important breakthrough recently. Last October, it was first put on the archive by Ranga and Professor Ike Silvera of Harvard University, and they claim they have discovered or attained metallic hydrogen system. And I remember in 1989, Professor Silvera invited me to give a talk at Harvard, and I asked him what he was working on, and he told me he tried to realize this feat. And so he has been working on this for almost the last 30 years. And in fact, along the way, has discovered many interesting phases of hydrogen under pressure. Yeah. So today we're going to hear from his postdoc, who is the first author of this paper just published in Science in January. Okay. And so Ranga, he is a postdoc from Harvard, and he was a postdoc also at Washington State, right, a couple of years ago. Yep. And you also get your PhD degree there, right, studying solids under high pressure. And the title of his talk is Pressing Hydrogen to Exotic Quantum States.
All right. Thank you very much for the introduction. So, as you see, so I'm going to talk about, so this work has been done in roughly around past 6 years. So all the materials right here I'm talking about, which I've done in past 6 years. The talk will be not too technical. Try to be very simple as possible, and maybe new to some of you. It touched the field of condensed matter physics, solid state chemistry, and material science and engineering, all these areas. So the picture you're seeing right here is the apparatus called diamond Anvil Cell, which we use to generate really high pressures. So 2 diamonds right here sitting opposite to each other, and in between you have this metallic gasket, which is going to be your sample chamber. So just to give a rough idea, so this is the device that we use to generate really high pressures. So I've been talking about the things we can do by using this device. So before I start my talk, I would like to acknowledge people who behind this work. My current advisor, Professor Isaac Silvera, so his guidance and all this teaching, and fellow my group members, and the scientific discussion from Professor Neil Ashcroft and Raoul Hoffman from Cornell, and the Graham Macklin from University of Edinburgh, and Dr. Bosted from Carnegie. And then the CNS, the Nanoscale System Lab in Harvard, and all the funding agencies. So we had a lot of private discussion about hydrogen under extreme conditions. So one time when I talked with Professor Neil Ashcroft, one thing that he said is, it's very motivation. At that time, I was a young graduate student. He said, if you want to really discover a new state of matter, cool it down, or subject to really high pressure. Whatever it is, cool it and squeeze it. That's what he was saying. So since we are talking about materials under extreme conditions at a very higher pressure, so we need to get some units into place. So the standard units we have, atmosphere, and then that's roughly equal to a bar, and then you have some English units, and then 1 atm roughly is the international standard unit that we use is a gigapascal. 1 gigapascal is roughly equal to 10,000 atmosphere, give or take. And 100 GPa is 1 megabar. So these are the units we generally use in these kind of experiments. So there's another calibration which happened to be a very interesting one. It's the center of Earth. the pressure of the center of Earth. It's been measured, estimated very accurately. It's 3.6 million atmosphere or 360 GPa. And this kind of gives the idea that the experimentally people can achieve in a laboratory pressure. People can now, like up to now, people have been consistently achieving the pressure of 360 GPa, roughly around a center of Earth, pressure of the center of Earth. So in terms of in terms of understanding what's really happened to a material when you squeeze it from 1 atm to a 3.6 million, like to understand, like it's enormous amount of pressure, right, going from 1 atm to 3.6 million atmosphere. So what really happened? How do you understand? How do you conceive this kind of thing when you apply really pressure to a material? So one thing easily can see happening is volume decrease. If I give you some examples, solid hydrogen, the volume decrease is a factor of 14 if you go from here to 1 atm to 360 GPa. And hard metal like iron, factor of 2, and water, factor of 3, and alkaline metal, like factor of 5. So the volume is really compressing. You're compressing the empty space in a material. And I give you another interesting example, which probably everyone in this audience knows about, is carbon and graphite. Graphite is the most stable form of carbon at ambient conditions. But if you subject a little bit of pressure, if you apply a little bit of pressure, it goes through diamond, and that's the most stable form of carbon at these conditions. So it is interesting to understand and interesting to know why carbon is stable at ambient conditions, why it's not less stable at higher pressures and higher temperatures, why diamond is very stable at higher pressures and temperatures. So it's not really a surprise, it's the densities. If you look at the density of the graphite is 2.27, but the diamond is 3.5 almost. It's much denser than carbon. So under pressure, the driving force to make material more denser, to get into more dense. So how do you get into these high pressures? So here's a simple cartoon. This is called the diamond anvil cell, the apparatus. They have two diamonds sitting opposite to each other. And in between those two diamonds, we put a metal gasket and this pre-indented gasket so that it can have the shape, taking the shape of the diamond and you can make a sample chamber right here. So by applying force from top and bottom, you can generate the pressure. So how big is this? How much small? How big is this sample? It's depend on the pressure you want it to go. So the pressure is force divided by area. The lower the pressure, lower the area, higher the pressure you can get. So generally, in my experiment, the experiment that we are doing, the size of this tip of the diamond is like 30 micron culottes. So we call here culotte, and here is a table, and 30 microns. So depending on this culotte size, the pressure that it can achieve can be limited. So for example, if you use a 100 micron culotte, you can go to 200 GPa. If you want to push higher than that, you need to get into a really small culotte size. So this is going to be the sample chamber where you apply pressure and squeeze the materials. So there's another way of generating really higher pressures, as is the dynamic compression. You can use the shock wave. You can subject the material to really shock wave and generate really high pressures. So this is, you've seen, is the gas guns. So you fire a bullet to a metal steel and create a shock wave. This is from my previous institute where I did my PhD. So generate these huge guns to generate really high pressures and study material under extreme conditions. But in this way, you can get really higher pressures, but your time scale is very limited. So you have a very small time window to this experiment. And also, when you do that, you just shoot up with the temperature too. So you go higher in temperature as well as when you go up in temperature. So you're more of getting into a liquid state and study of liquid-liquid phase transition, or the planetary science is how this hydrogen or helium behave in giant planets. So it's a different regime that you're going to study. To bring it down to like very low temperatures and high pressures, you need to study a diamond anvil cell. So this is static compression. So you have a lot of time to do all the diagnostic you wanted to do. So, so to give an idea, so I'm trying to make it as simple as possible. What's really happened when you squeeze material? So this is a picture of a Boston subway, a red line. So what I'm going to do is, this is when you walk into a subway, so you have a fixed volume, right? and I'm going to vary the density of inside this fixed volume by adding people to there. So when it's not rush hour, you have only few people right there. So it just, people tend to sit very apart from each other, unless they're a couple, they sit too close to each other. So when you squeeze materials, you increase in your neighbors, you increase in the nearest neighbors. It's just similar to something like this. So when you get into a rush hour, you're getting more people in there, right? So you're squeezing and packing the material. So here, this is the no pants day, they call it. I don't know what's really happening on that day. So people start to go subway without pants. So it also nicely fit to this analogy, because when you squeeze material too hard, at some point, even the electrons can strip apart from the atom and delocalize. It gives the good analogy of what's really happening. But on the other hand, like in our case, we fix the number of atoms, change the volume. It's the same thing. You can think of you have a fixed volume and adding more people equal to the atom. So you increase the density by that way. So you have a rule of you have rules, it's in the fixed volume. But unless you go to India, you increase the volume too, so in a different way. So that's another way of breaking the rules, which can happen in high pressure. A lot of rules is breaking in high pressure. Or there's another way. This is a picture of subway in Tokyo. So you can hire people to apply pressure. You can use some other people to push them inside, pack them in. So this is kind of idea which I'm going to talk later. The chemical pre-compression. So this is the idea coming from to explain the chemical pre-compression by using this. All right, so let me give you a little bit of few examples so that you have a kind of idea what's really happening when you apply pressure. So when you apply pressure, the P delta, we change the P delta V, the compression energy can be comparable to really the bond energy of those materials. You can generate 100 to 1,000 kilojoule per molecule by going into a really high pressure, like 100 GPa roughly. So if I give you an example of carbon dioxide, so carbon dioxide, it's a gas, right, at ambient conditions. But it's very, in terms of why in the periodic table, so you have SiO2. Why CO2 is not similar to SiO2? SiO2 is quartz, but CO2 is a gas. And on the other hand, nitrogen, why it's not similar to the antimony or arsenic, right? So periodic table should be good for something. So, but if you apply pressure on carbon dioxide, it goes to a quartz-like structure, very similar to SiO2. It's give up the so carbon dioxide to start with the double bonded, right? But here you have four-fold coordinated extended structure, like 3D network structure. So you increase when you apply pressure, you increase in the coordination, you increase in the valence of the material. It's the same, if you look at this is the synthetic condition for this. If you look at the oxygen form this beautiful scarlet color, red oxygen. It's make this clusters, O8 clusters under pressure. And if you look at another example of nitrogen, so nitrogen, one of the strongest triple bond you have, almost 1,000 kilojoules per mole, and they give up this energy to go to a single bonded. This is to start with the triple bond nitrogen, is give up that energy and goes to a single bonded nitrogen. So these kind of transformation really fascinate me, like why these kind of things happening under pressure, the crazy things that we can think of. On the other hand, all the energy on this triple bonded now, are distributed in this single bonded. So when you release it, you can get it back the whole energy. So you make creating an energetic material, creating a high density material. And this material, for example, is carbon dioxide, is a super hard material. And it's optically nonlinear. And oxygen goes superconduct. And it's magnetic, all of you know, the ground state is triplet, but it goes non-magnetic and become superconduct. So all kind of different phenomena can happen under extreme conditions. So studying this is really a fascinating field. So what really happened, if I give you in terms of a little bit of different way, when you squeeze material, in the beginning what happened is you're really squeezing the empty space. You're really squeezing the van der Waals space. You're really attacking you really don't need to attack. You're really going through this attractive part of the potential. But if you compress further and further, then you are going to the repulsive part, where you're going to get the electron to delocalize and get all sort of insular metal transition, superconductivity, all this quantum phenomena that you can think of. And it's in a way, it's a derivative energy of volume. So it's in a way you are really you're modifying the energy landscape by applying pressure. You're really changing the energy and you're trying to manipulate the twin, the bond, and everything, so that you can make the material that has unusual properties. So another interesting property that can be happen under pressure is which happened to be, as a physicist, is much more interesting for me, is if you take an insulator, we have a wide bandgap insulator with have a gap. So, you know, let's say very transparent, very material, and then when you subject that to a pressure, at some point the interaction between empty band and the valence band going to cross each other, then you're going to have an insulator to metal transition. So this is something that really interests me, and how we can make metal out from any other materials, any materials that we can think of. For example, xenon. Xenon is a noble element, right? It's a noble gas. Who would thought that it can be a metal? If you subject to xenon and to a pressure at 130 GPa, it becomes metal. And it's not just a metal, and it's a transparent metal. The plasma frequency is really low in this one. It's 0.4 electron volts or something. So noble gas can be a metal, and also you can make new bonds with noble gas and some other materials. Recently there was a paper, helium bonded with the sodium. So different kind of new bondings can happen. And oxygen, as I mentioned before, it can go to a superconducting transition. This is one of the molecular superconductor that exists. And iodine go to a insulator metal transition and become atomic metal, and so is the cesium iodide and oxygen superconductor. So virtually you can think, if you subject every material to pressure, it can transform to a metal. But not everything. But some goes in the opposite way. It's just so fascinating to understand. Why? So, for example, alkali metals, sodium or other material in alkali originate. When you squeeze it, it goes transparent. It goes to insulator. So does the lithium. Lithium superconductor, but at higher pressures, it goes to semiconducting to insulator transition and goes back again to a metal. So this kind of a change in the paradigm of the bonding shifting. The reason for this one is that they electron make a bond in interstitial sites in the sodium. So when you squeeze to really higher pressures, and that gives you a new bonding and become transparent. So another interesting thing, as I mentioned in oxygen, is superconductivity. So before the superconductivity, the highest TC recorded for the Cooper superconductor under pressure was 164 GPa. It was 130 Kelvin, and then when you subject to pressure, TC increased to 164 Kelvin. So that was the record before last year. The last year we found a hydrogen disulfide, when you subject to pressure, it's superconductor at 203 Kelvin. It's the highest TC we know. And it's follow the BCS model. So the BCS model predict only you can get a higher TC of like 40 Kelvin or not more than that. But here we have 203 Kelvin TC on H2S. So the real sample is, they call it H3S. It's decomposed and form H3S. So H3 is the real sample that superconduct at 203 Kelvin. So under pressure, you can have this enormous variety of thing happening when you superconducting, insulator metal transition, high energy density material, super hard material, optical nonlinearity. You can think of all sorts of different phenomena. So here's going to be my talk. I gave a little bit of introduction what we're going to happen under pressure. So the first part of my talk, I'll give you the new phase transition on hydrogen, and I'll discuss about the observation of the metallic hydrogen and some of the new superconducting polymers. Okay. So for hydrogen, why hydrogen is so important? So as in the introduction, so this has been predicted a long time ago, nearly over 8 years ago. If you subject to pressure, Vignan Huntington predicted that it can dissociate and form into a transition to atomic metal. So if you look at here, this is how hydrogen at ambient conditions is an insulator. And it's far apart from those molecules, roughly around 3.8 angstrom. But as I mentioned here, when I squeeze the material, they get together close and close and closer. At some point, the band going to overlap and goes to an insulator metal transition. Even it can dissociate and become a metal, so you don't have bound states. So the predicted densities are around like 14-fold, and in terms of pressure, it's roughly around 400 and to 600 GPa. So hydrogen is a quantum solid. So you have, this is de Broglie, the quantum parameter. So if we in quantum solid, it's a higher lambda value, so the kinetic part is really high. So you get really highly anharmonic phonons here. So very interesting properties hydrogen has is the very first one attract, at least my attention is it can be a room temperature superconductor and follow the BCS model. And it can be a superfluid at metallic state. And also it's a highly energetic material. It's 35 times much more higher than the TNT. And it can be a zero temperature quantum fluid. Its 0 point energy is really high. And it can have a Bose-Einstein condition with condensation without no pairing mechanism. And in terms of planetary science, the interiors of the giant planets is thought to be having liquid metallic hydrogen revolving around and give this dynamo effect to high magnetic fields. So in terms of fundamentally and application-wise, it's very interesting material to study with. So that's why we focus on hydrogen and to get into really high pressures and make metallic hydrogen. So people have been trying this one for over the years, like many years. So here's, I just plot the year and the pressure, the metallization pressure. So this is where I first predicted. The red one, red squares predicted, and the blue ones are the experimental observation. So 25 GPa, but they got the density roughly correct. But people achieved it, they didn't see any metallization, and again, back again. Every time when experimentalists get into a pressure that they predict, theories change the pressure. Nothing happened, and theories change the pressure. So it's keep going up and up. And this is where roughly they stand. But liquid metallic hydrogen has been observed before at lower pressures, but at really high temperatures. So in 1996, the Nellis group, they made the liquid metallic hydrogen using shockwave. And in our lab, in a static condition, we made last year liquid metallic hydrogen at a modest pressure, like around 150, 40 GPa, but around 200, 300 Kelvin. So you go up in temperature. So you make the liquid metallic hydrogen. So the solid metallic hydrogen at low temperatures has never been observed before. So if I give you a little bit of background on hydrogen, so this is the low temperature phase diagram of hydrogen. So you have four new phases people have been found over the years, most of them found by in our lab, and this is the recent one which was found in Max Planck group in Germany. So we have a low pressure phase. It's a SCP structure. It's a freely rotating molecules. And then if you go up in pressure around 110 GPa, you get the broken symmetry phase, which is stable to up to 150 GPa. And if you go up in more pressure around 150 GPa, you get this phase 3, which has a very interesting property. It gets really strong IR activity. So it's homonuclear molecule. It's hydrogen. There's no dipole moment, but you get induced dipole moment here. You get really very strong IR activity here. It's induced IR activity. Your electron cloud. It goes like something like you have hydrogen. The electron cloud kind of going to one side, getting more charge, and other side is less charge. So it gives this induced dipole moment, which is interesting. And this phase that people thought that, oh, then this is never going to be a metal. It won't be any metallic nature. But the predicted pressure was somewhere around here. And the phase 4 is another interesting phase. It was recently found at room temperature compression. It says it has this graphene-like phase, like graphene-like layers. The hydrogen has you ring molecules like a graphene on layer the structure. So something interesting structures to study. So all those things are studied by a spectroscopic technique. It's difficult to do X-ray on hydrogen. So none of these phases are metallic, up to 360 GPa. This is where people have been stuck over the years before you're getting. So how do you determine a phase transition in materials like hydrogen? So what you're seeing in this graph is pressure versus the frequency. IR, the vibron frequency of, so hydrogen molecules, so you have a vibron, the stretching mode of the hydrogen molecule. So you track that under pressure. So when subject to a new phase transition, you will see disappearing or appearing of new peaks. When the symmetry change, you will see the change, either discontinuity or disappearing all those modes or appearing new modes. So if you look at here, the vibrons we have right here all disappear, and then new vibron happen here. So there's clear indication of this disappeared and new appeared, and has a huge difference here in terms of frequency. It's a clear indication of the phase transition. This is how we identify new phases in material like hydrogen, which is difficult to do X-ray. So I'll give you a little bit of experimental setup we have. So we do Raman and high R spectroscopy at low temperatures. This is our setup. We can do 2 Kelvin and IR and Raman spectroscopy. We use a backscattering geometry. Sometimes we use forward scattering geometry. And diamond is transparent, so you can use all kind of sort of spectroscopic technique, Raman, IR, and even X-ray. And if you want to heat the sample, you can couple with the IR laser, and you can bombard with the photon and heat the sample. So you can do high temperature studies too. So that's very localized heating. Or you can heat the whole diamond anvil cell. Diamond is a very good heat conductor, so you can really put a lot of heat into the sample by using diamond and heat it up. But that's kind of limited in temperature region. And also you can put 4 electrodes and measure the conductivity. So what you're seeing here is 55 GPa. This is a reflective sample. This is a metallic sample, and 4 electrodes attached to it, and squeeze it so that you can track, you can change the transport, you can measure the transport properties. Or also you can use the magnetic measurements. You can do, this is the size of the coil we used. I just put it in here so that you can have an idea of its size. So just small samples. So you have to make sure that you have enough filling factor, so you make those coils very small and sit around this diamond area right here, and then you can use magnetic. So if you have superconducting transition, we can do magnetic measurements. So people have been going to a 360 GPa, found new phases, but we tried those decades of all the experiments to how to get into the really high pressures and make it metallic hydrogen. So how did we get into really high pressures? What did we do different? So the one thing that we did was, the failures of diamond is one thing is the microsurface defects. So when you have a nice polished diamond, but if you look at through this under the atomic microscope, you can see defects. So we use the RIE technique to remove those defects and make a nice smooth surface, so that it will not prevent hydrogen getting in there and breaking the diamond. This is diamond look like after RIE. So another thing is hydrogen is very diffusive. It goes into the diamond and it cracks the diamond. That's going to prevent us getting into really higher pressures. So we found a way to prevent that happening, and we used the aluminum coating put on top of this small alumina coating on the diamond, so that it will prevent diffusing hydrogen into diamond. And also, so we use this laser spectroscopic technique to measure Raman and IR, Raman especially, to track the pressure. So laser shock can break the diamond. So we managed to use the minimum, getting the better Raman system, designing a new Raman system, so that with the small laser power, we can really get a strong signal, so that we don't have to use much power to get the signal, so that otherwise we're going to break the diamond. So this and modifying our apparatus, getting perfect alignment, and make sure that all this instability is not there, and refining your apparatus, we were able to generate really high pressures like 500 GPa. So while we were doing this one, we observe a new phase transition. So I'm going to give you a little bit of idea how we determine the new phase. What is this? This is the frequency, and this is the absorption you're seeing here. And I mentioned that to determine the new phase transition in material like hydrogen, you track the vibron, and if you see it disappearing or appearing new modes, which indicating of the changing of symmetry and seeing a new phase transition. So if you look at here, this is the vibron of the phase 3, the IR activity, the strong peak. And when you squeeze at around 345 GPa, it gets really broad, and then next pressure point, 355, it disappears. This is totally gone, and then 2 new peaks appear, and there's another small bump here, if you can see it here, right here. So this is a clear indication of new phase transition. So we named this one H2 pre, indicating the pre-metallization pressure, hopefully. So we observe this one to all the way to 420 GPa and all the way to 495 GPa. So if I plot the pressure versus the vibron frequency, you can clearly see there's a discontinuity here, disappear of this mode, and the new 3 new peaks appearing right here. Clear indication of a phase transition. So to understand this one, what kind of phase is this one? So we we look into the theory, and this is the theoretical phase diagram they have predicted. So they predicted around somewhere around 340 GPa or 370 GPa, there can be a new phase transition. So this is the enthalpy studied. So they come up with around like 370 GPa. You can have this new phase transition called CMCA12, and it has two main characteristics via IR vibrone, 3223 and 35. But I just want you to point it out and just look into this and the difference between these two peaks. It's around like 360 inverse centimeters. So if you go to my new phase right here, the difference between these two peaks, 370. But these two peaks are much softer than this one, right? This is around 32 and 35. This is around 29 and 33. This is a little bit different, like it's softer than what the theory predicted. And the problem with the theory is that it's difficult to get this calculation right because of the anharmonic nature of the hydrogen. So you have to do the anharmonic correction. So if you do that and the 0-point energy corrections, you probably can bring it down, softer this one. And probably this will probably be the same CMCA12 phases that theory has predicted. In terms of how it behaves under pressure, it's very similar to what we observe. So it has the same differences and the same pressure dependence. So it's not exactly the CMCA12, but that's the best guess we can give. So the story starts from here. So while we were doing this, squeezing this to really higher pressures many times, so what we observed is, so at lower pressures, this is a picture you're seeing as 200 GPa from the transmitted light. So it's transparent. This white thing you're seeing in the middle is the transmitted light, and it's insulator. It's a transparent hydrogen. But if you squeeze a little bit further, another 200 GPa, this is only from the reflected light, and you see opaque hydrogen. So what you're seeing right now here, this shiny area, is the gasket that I was talking about. So you have two diamonds squeezing them each other, and in between you have this metal gasket. In the metal gasket, you drill a hole and you load your sample. So if you look from the top view, you will see the circle of rhenium, whatever the gasket material you're using. We were using rhenium. And then in the middle, the central area is your pure hydrogen sample. So it's opaque. It doesn't light pass through it. So indicating something is happening. This is after we saw the new phase. And if you squeeze further, you will see it get reflective. This is from the reflected light. So the black area is now almost as transparent as rhenium, or even higher than that, right here, right? So visually, you're suggesting that band gap is closing. So you're seeing insulator metal transition. You can see band gap is closing. So how do you prove this one? So we fit this one to a Drude free electron model. The theory predict that it's closely follow the Drude free electron model. So from there you can get the plasma frequency and the relaxation time, and you can calculate the conductivity, and below the plasma frequency it's reflective, and above the plasma frequency it's transparent. And so the diamond is touching the hydrogen sample right now. So you have hydrogen, metallic hydrogen, and on top of that you have a diamond layer. So you know the refractive index of diamond is 2.41. So from using that, you can get the reflectivity of hydrogen. So hydrogen reflectivity gives in this equation. So you have plasma frequency, relaxation time, and you substitute here, and ND you know, 2.41, and then you can fit this to Drude model. So here are the data that you're seeing is a Drude fit for the different wavelength. So we did from 400 nanometers to 1550 nanometer range. So what you're seeing right here is the blue dots are the 5 Kelvin, red are the 83 Kelvin reflectivity. So reflection is as high as 91% at 5 Kelvin. And to comparison, we measure the reflectivity of rhenium. So this curve you're seeing is the ambient condition measurement done by others. And these are the measurements have done by us. So in comparison, we have very similar, which matches fairly well. Rhenium, so indicating that whatever we are observing it's real measurement. And from there we extracted the value for plasma frequency and relaxation time. It happened to be the 32.5 electron volts, It's one of the highest known plasma frequency, and from there we can get the electron density. It's 7.7, roughly around 7.7, and the theoretical estimate is around 6.6 to 8.2, so which is well within the theoretical estimation. And from there we calculate the conductivity is 1.46 to 10⁷ sieves per meter. It's very metal. So we made the atomic metallic hydrogen. So the density right here matches with the atomic density if we go to dissociative transition. So we have atomic metallic hydrogen. So if you compare these to other alkaline metal in the same column, so you have lithium, sodium, and potassium. They have 7, 5, and 3. So they have remarkable contrast compared to the other alkaline metals and here. So that's something interesting to study and see why these kind of changes happening here. And if I summarize the hydrogen part right here, so what you're seeing, this is a new phase diagram of hydrogen at low pressure, low temperatures and higher pressures, temperature up to 360 GPa. So here you have the phase line of phase 2 to phase 2 to phase 3 phase line right here, and this is phase 1 to phase 2, and this is at higher temperature, and this is the measurement done by European groups and the German group, Max Planck group and the University of Edinburgh group. So this is the phase transition from phase 3 to phase 4, and people have been seeing some new phase transition recently around phase 5, but this has to be confirmed. And then these are all our measurement. You can see the new phase line here, and whatever the new phase we observe are being observed by the other group, the Erimetz group of Max Planck. He observed the same thing. He was squeezing at room temperature and coming down in temperature. So he was seeing the exact same thing we have been observed right here. So you can kind of match the phase line right here. And if you go up in more pressure, so you get this metallic hydrogen. So in summary, so we have reached to the recorded pressure 495 GPa, and we observe new quantum phase transition, and the Drude electron model gives you the parameters or plasma frequency and electron density, and we produce the Wigner-Huntington dissociative transition to atomic solid hydrogen. So this solid part, we really don't have the clear evidence for this is a liquid or solid. So visually, we can't really tell it's a liquid or solid. To prove that one, either we have to do Raman or X-ray studies. Doing Raman is really difficult because it's very shiny and has a skin depth of like 6 nanometers. So you really need a very perfectly aligned system to get it. That's something that we're working on it. Also, there's some discussion with the Argonne National Lab to do X-ray studies. They were saying that they can really give a shot. They can get a really intense beam for 2 micron, 3 to 2 micron size of beam size, so that we will not get any perturb from the rhenium, other metal around the sample area. So that's something to really prove whether it's a metal, it's a solid or liquid. So in terms of future, so this is something that, so if it is, so one first thing as I said, but it's a liquid or solid. So that's something interesting that you want to check. And if it is solid, does it superconduct? As theory predicts, it's theory predicts that it can be a room temperature superconductor. And if it is room temperature superconductor or whatever, it is superconducting, is it going to be, what type of superconductor? Is it BCS? Oh, there's a typo, sorry. Is it BCS model or something else? So this is something, the interesting question that we can address right here. And if it's a liquid, will it be a first liquid metal? So 0.8 is so high, and even at T equals 0, it can be a liquid. So if you look, it can be, if it is liquid, it's a liquid superconductor or superfluid, which people have been predicted. And all those new represent the new quantum state of matter. So this is a very interesting system to further explore and measure these new exciting properties. And also quantum melting and how the melting line and the metallization is happening, which kind of pressures and temperature scales. Like for example, if I draw you quickly hydrogen phase diagram, this is pressure and this is temperature. You have all new phases right here. This is phase 1, phase 2, phase 3, phase 4, the new phase we observe, and metallic hydrogen. And the melting line goes something like this. So what's going to happen right here? How it's going to meet here, the solid and melting line coming from there. So those are very interesting unanswered question to study. And also it said it's metastable, just like diamond. If you release the pressure, it's going to stay there as it is. That's something we are right now currently checking, the metastability of this sample. And is it highly energetic, and check those properties. Those are very exciting new future direction on this we can address. So the last part of my talk, I'm quickly going to discuss some of the exciting new results on new superconducting polymers. So the interest came from the carbon and sulfide. So if you look at this diagram right here, this is the free energy and the volume. So at around like 70 GPa, sulfur free energies almost have 2 electron volts. So you, by applying pressure to going into like a pressure of 700 GPa, you're really tuning the bond length, the energy of this bond length. If you look at carbon and sulfur, it's 2.6 electron volt, carbon-carbon 3.6, sulfur 2.7. So you're really tuning the bond energies. So can we use this one to make, this is like a highly compressed like sample like carbon disulfide. Is it going to be like a molecular alloy of carbon or sulfur? So in terms of those mechanical energy transformed to tuning the chemical bond, it's interesting materials to subject. If I give a little bit of background, this material has been studied extensively like many years ago. This is one of the first sample, Bridgman, who got the Nobel Prize for high pressure experiment in 1946. He studied and he discovered this Bridgman black sample called Bridgman black. So Bridgman black is the threefold coordinated carbon sulfur atoms. So you have a linear CS2 molecules, but when you pressure it to higher pressures, it transforms this polymer. And if you subject to more pressure, it can go to a CS4, the fourfold coordinated carbon disulfide. So this is roughly the phase diagram people have been studied. So this going into energetic material and also increasing the coordination from twofold to fourfold. So theory predicted something interesting. So we wanted to study. And so visually, this is very similar to what we observe in hydrogen. At low pressures, it's a liquid and it's transparent. But applied to higher pressures, it goes opaque and reflective. So visually, you're seeing that really it's transformed into a metal. So while we were doing this one, you see the changes in this is Raman spectrum, and the intensity you are seeing here. Right now, what you're seeing is vibrational spectroscopy, lattice modes, and the stretching vibration, and the overtones. And around some pressure, everything is disappear and get new peak, broad peak, and that two broad peak merge into one new peak. So this is also indicating there's a new phase transition right here. And if you squeeze further, you will see this. This is the pressure versus Raman frequency right here. So you go up in pressure, you can see all these modes disappear, all the stretching modes and lattice mode disappear, two new lattice modes appear. And then if you squeeze further, those two modes bring it to one and have one peak, which this Raman frequency is corresponding to carbon sulfur single bonded frequency. So it's kind of indicating that as theory was predicting, we are getting into a single bonded network structure of carbon and sulfur. So then with this, we did conductivity measurement. We put 4 electrodes and measure the conductivity. And if you look at here, the pressure versus the resistance, you can see it goes like an 8 order of difference in resistance while squeezing into really higher pressures. It goes from insulator to a semiconductor to a metal. And here you are seeing at low pressures it's not shiny, and get into really high pressures, 200 GPa, it's very shiny. It's shiny as electrode, platinum electrodes. And low temperature resistance studies also show that it's going into a insulated metal transition. So if I put all this phase transition on top of the resistance measurements, so it's nicely matched with the new phase that we were observing right here, the new CS4 phase, fourfold coordinated carbon disulfide phase. The new insulated metal phase transition is well within the phase 4 of the carbon disulfide. And for understand this one further, we did this is kind of getting an amorphous structure. So to understand this one further, so we did the X-ray measurement. So from the X-ray, we did the PDF analysis and get the structure factor and get the first nearest neighbor coordination. And from that, you can calculate the ratio of first nearest neighbor and second nearest neighbor. It's like 1.64. It's very close to a tetrahedral structure, which is close packed structure. So it's kind of given assurance that we are making a 4-fold coordinate carbon disulfide. And we did some diffraction profile calculation. So we have two different structures candidate based on the carbon dioxide. From the diffraction profile, if you look at right here, the tridymite structure, it has a very similar, like the shape of this is very similar to what we experimentally observe right here. So it probably, we don't have the clearly what type of structure, but the best guess is we have is somewhere around something like tridymite structure, 4-fold coordinate. And then the band structure calculation shows also it's metallic, both structures. The most favorable candidate probably be the tridymite structure. And so the another question that you ask, can this be like a superconductor like others sp elemental metal? Sulfur is superconduct. So with carbon dioxide, this molecular alloy film can be superconducting. So just to test that, we did the conductivity measurement at low temperatures, and we see a clear indication of a drop in resistance, superconducting phase transition around 6 highest TC was 6.02 Kelvin. So it's not that high as like room temperature, but it's high enough to this kind of material to have interesting phenomena. So, and the magnetic susceptibility confirmed that. We have this graph is TC coming from the magnetic susceptibility and the resistance. Red are the magnetic susceptibility, and the blue ones are the resistance. So from both you can think of confirming that it's superconducting magnetic measurement and the conductivity measurements. So, and the low temperatures, this is interesting enough, it goes to another phase transition. So if you do the X-ray studies on low temperatures, you can see when you lower the temperature, this is going from 300 Kelvin to lower temperature, around like 40 Kelvin. There's a clear change in the profile. There's a new peak appearing right here. So this peak and the ratio between the first nearest neighbor and second nearest neighbors give the roughly ratio of octahedral structure. So it's going now, so I was telling, when you apply pressure, one thing happening in under pressure is increase the coordination. To adapt to the higher pressures, to adapt to a higher pressure environment, what you do is you increase the coordination. So the carbon disulfide, to start with, it's a 2-fold coordinated, but under pressure, it's got 3-fold, 4-fold, and even for 6-fold. So you increase the coordination to adapt to higher pressures. So interestingly, so all this material that we form is stable. We can bring it down to ambient condition, still have the metallic properties, but not superconducting. We haven't really tested that one. So if I summarize the new phase diagram of carbon disulfide, it goes from insulator to metal transition, and which I haven't shown you here is it also goes through a magnetic transition, antiferromagnetic transition before it goes to superconducting transition. So it has a superconducting antiferromagnetic transition, and it goes from 4-fold to a 6-fold coordination under pressure. So this is an interesting sample to study, and we want to see the systematic behavior of this sample. So we studied not just carbon disulfide, we studied the silicon disulfide, germanium disulfide, all this, the group 4 and 6 sulfides. So all these materials has all the similar properties. So, and not even just silicon dioxide or silicon disulfide or germanium disulfide. Another interesting thing you can do is you have a carbon dioxide and you have a CS2. What if you remove one sulfur and add oxygen? You make intermediate state of carbon dioxide and OCS. So how is that going to behave? This oxygen, role of oxygen and sulfur. Why CO2 is not a metal under pressure? We put into a pressure of like 250 GPa. It's transparent, it's insulator. But carbon disulfide at around like 50 GPa, it become metal, but not carbon dioxide. But if you replace one oxygen with sulfur, how is that going to affect to this insulator metal transition under pressure? So then you bring down, so CO2 is not a metal up to 250 GPa. CS2 is a metal at 50 GPa, but if you remove the one oxygen and add sulfur, it becomes metal around 110 GPa. So this is a conductivity measurement. You can clearly see an insulator metal transition. But this material goes back to to insulator. It doesn't stay as the conductive state. So here you can see the pressure and the vibron frequency of Raman shift, and this is the resistance, showing the 7 order of drop in resistance right here, and these are the frequencies, you're changing frequencies while you're going through the pressure. You're clearly indicating phase transition. And all the other materials, carbon disulfide, silicon disulfide, germanium disulfide, tin disulfide, all those materials has the same behavior and goes to insular metal transition superconducting, and these can be recoverable. So we kind of found a new class of polymers which has properties of superconducting and metallic under extreme conditions. This is something that we need to further studies. If I summarize this one, so under pressure, it goes to an insular metal transition, and then it goes to a superconducting transition as well. And it goes, as I mentioned, goes from 2-fold to 4-fold to 6-fold coordination. And all these group 4-6 sulfides show the exact same behavior, including the one oxygen. If you remove one sulfur with the oxygen, including that, has the same behavior. But only that one doesn't really stay as the metal if you squeeze material. So that's all I have to say, and I like to finish my talk with a positive note. So this is the William Gladstone, is the English finance minister, and he served as the prime minister for 4 times. So Michael Faraday, one of the famous scientists, one time when he found the electricity, Gladstone asked from him, this is very interesting, but what's the practical use of electricity? And the Faraday's response is priceless. So what he said is, I cannot say what the practical use, but they might be, you might be taxed it one day. So this is a hope doing the fundamental science, even though we are in the regime of really higher pressures and people can ask, so what's the use of, but there's a hope of we can bring down these materials to higher pressure, ambient conditions and study and make new materials. Thank you.
When someone in the audience asks a question, could you repeat it?
Sure.
So that
Yeah.
I can catch as well.
It's okay. I have 2 questions.
Sure.
One is just a short request for clarification, and then another question is somewhat longer. I would ask you to speculate about something. But first, a clarification question. So you mentioned in your discussion of carbon disulfides and nuclear and polymer. So I wonder what's the chemical formula? Do you mean that C?
Yeah.
S or N or what?
Yeah, the chemical formula for carbon disulfide polymer is, I can write it down right here. This goes carbon double bonded sulfur, sulfur, carbon double bonds. Yeah, this is the structure.
And so what pressure this becomes stable? Because normally you know that CS2 is just a nice liquid.
Yeah, nice liquid. And yeah, so it's so you can form this one around like 8 GPa, and once you release it, you have it. You can have it at ambient conditions. It stays there as a black. So we call this one Bridgman black. So Bridgman, Percy W. Bridgman is the first to discover this material. So he named it as a Bridgman black, and once you release it, you can have this Bridgman black in hand.
Okay, so another question, it's probably a request for speculation because your metallic hydrogen is a very new thing, but we know that even though hydrogen is in the same column of the periodic table as alkali metals, at normal conditions its chemistry is very, very different from them. And so I wonder what happens, and one manifestation is it's not a metal and they are metals. So I wonder what happens, what do you expect to happen with this metallic hydrogen? So would its chemistry be like that of alkali metals,
Or the
say
halogens.
at ambient pressure, or would it be like chemistry of alkali metals at the same high pressure? In what comparison would it be with alkali metals in that respect?
Yeah, so in terms of what kind of, someone can think hydrogen as is like, half empty glass or half filled glass, right? So you can put it in the halogen column. It's chlorine, bromine, and that side, or within hydrogen. I think the Russian periodic table, they put in both sides. So
Should not put in any one of these.
yeah, or maybe put it somewhere in the middle. So, the comparison of the sodium and other alkali metals, so it has a very different plasma frequency. So other material, those alkali metals has like 7 and 8 electron volt, but this one has 32 electron volt plasma frequency. And none of those alkali metals superconduct at really high pressures, high temperatures. The highest TC, only lithium superconduct, which is at 20, somewhere around 20 Kelvin. But none of the other materials superconduct. People have trying it. So in terms of that, it's really different in terms of those plasma frequencies and in superconductivity. We don't know whether it's a superconduct or not yet. But if it really does superconduct at really high temperatures, it's very different from the rest of the alkali metal. So maybe we need to put it in somewhere else, not in the first column.
So you don't expect it to be like alkali metals, no matter what the pressure is.
We were, to be honest, we were expected to be something similar to that, but we are seeing a really very different than what alkali metals. So yeah, I mean.
So what is then about diagonal connection? So we know that lithium is like magnesium and beryllium is like aluminum. Maybe you would get hydrogen like beryllium, or you don't expect anything like that too?
Yeah, it could be even transition metal type. You know, we have all this. Some people have predicted about this Fermi liquid theory, some different predictions. So it can even put it into D block. So really, I mean, to be honest, I really don't know where you can really put, but it has all this sort kind of different properties. But yeah, even alkali metal or halogen. And on the other hand, halogen, chlorine expected to be metal, and bromine is a metal. It's color, right? So if you squeeze a little bit further, then it becomes metal. So maybe we can put it in that side.
I think there's an old Russian paper saying that if you remove the pressure, the material will
Stable.
bounce back to the way it was. Now, could you explain why that is and what the limitations are?
So what they predicted, that is a metastable material, like it's just like a diamond. Yeah, just like a diamond. So it's going to stay the higher density form what you're forming. It's going to stay there.
What do you think?
Well, in experimentally, we made this one at 500 GPa, right? And we now at 300 GPa, still it's a metal. So right now we are conducting an experiment. We are releasing the pressure, that's still stable.
So it's still sitting.
Right now it's sitting at low temperature and metallic form, even at 300 GPa. So this is something we are ongoing on experimentally. So we haven't really bring it down to a room temperature, a room pressure. So I can say with confidence, to range of 200 GPa, it's stable. Where it make 500 GPa up to 300 GPa stable. Yeah.
Why does that process go on so slowly?
So we were trying to be cautious. So you know the process called the cold welding. So when you squeeze, so you subject the material to really high pressure, you have this metal gasket we are using. So sometimes this metal gasket can bond to a diamond. So if you release the pressure too quickly, it can break the diamond, shatter the diamond. So you need to peeling it off slowly, release the pressure so that you. So this is just an experimental point of view. We are going slow, just to be safe. Yeah.
Thank you.
Yeah.
So I had a question about the numerical comparisons that you were making.
Sure.
So as far as I know, most people are predicting 1.2 terapascals for metallic hydrogen. So if you look at path integral Monte Carlo, path integral molecular dynamics, and a combination of Pickard and Needs' different DFT calculations using a variety of functionals, it's way, way higher than what you're predicting.
I'm not sure. So one of his recent papers, if you look at the 2002, so if you look at this paper, go check this one. All the predictions are around 400, 500 GPa, 400, 600 GPa. Which paper are you mentioning?
So Pickard and
I know.
Needs. So I think that's the same data that you're suggesting.
So this is Pickard. This is his postdoc by then. So this is from the Needs and Pickard's work. This is 2014. So this is what they're expecting. So if you look at here enthalpy, right? These are the three phase transitions they were expecting. CMCA 12 goes to CMCA 4 and go to atomic metallic phase at 465 GPa, right here. This is from their calculation. So here they're predicting the insular metal transition right here. So what we are observing right here. So it's fairly matching, I would say, in terms of theory, and even in our measurement can have a 30 plus or minus 30 GPa. So in terms of that, I think we theory and experiment matching agreeing each other. I think So these are, maybe you're looking at the earlier calculation. So these are very recent ones.
Right, right. So I'm thinking about the 2011 Nature paper
Okay.
by Pickard and Needs.
Yeah. So he has another one, 2007, which he was doing some of phase 4 calculation, which might be a very interesting paper to check, doing all these calculations.
What is the thickness of your alumina overlayer, and what's the thickness of the hydrogen metal? And how do you address concern that, I mean, alumina is not turning into a metal?
Yeah, very good. I'm glad that you asked this question. So one of the people who criticize, well, always you have a criticism. It's a good thing in science, so it'll advance the field. So some people think the alumina layer that we are putting is probably be the conducting. Probably it's transformed to a metal. So the alumina layer we put is roughly around 50 nanometers, but we have a hydrogen sample of 1 micron in size right here. So we have extensive experience on alumina. We have studied alumina to up to 400 GPa, and even not just room temperature, even at higher temperature. We heat the sample and cool it down and see all the behavior under pressure and temperature. So we haven't seen any indication of insulator metal transition in alumina. And there's some theoretical calculation on alumina under pressure. So they predict if you subject alumina to 800 GPa, it can be a metal. So we are at 500 GPa. We have very low pressure than compared to the Al2O3 metallization pressure. So on the other hand, even if it is, let's assume this criticizing people, they're correct, even if we become metal. So the layer is going to be really small. So we're talking about 50 nanometer, but at 500 GPa, it's going to be much smaller than that. Even hydrogen, we start at 10 micron size, but by the time you get to 500 GPa, it's like 1 micron. So even if you make Al2O3 a metal, it's going to be really thin enough. It will be transparent. The skin depth is so high, so you will see it's transparent. You will see through it. And on the other hand, you will not see. So when we do, I'll show you this picture. Yeah, in this picture. So this is, you have alumina right here. Okay, when you put alumina, we put alumina on the whole diamonds, everywhere in the diamonds, the surface of the diamond, you have alumina. So if you make alumina metal, you won't see this kind of clear boundary of you have a diamond gasket, you have a metal gasket, and you have sample. So the whole thing will be one shiny layer. You will not see the difference, the contrast in the material. And even right here, you can see the very, this image is not that good, but if you look at it in a computer, you can clearly see the boundary of sample, hydrogen, and then the gasket area. You will not see that one. On the other hand, even if it is become metal, it's thin enough, then it will be transparent, and you will not really see it. Yeah.
Since you can vary the temperature, are you able to infer the temperature dependence of conductivity or resistivity of hydrogen, of metallic hydrogen?
We have not done that yet. That's something to do in the future. We haven't put any electrodes and try to measure the conductivity of this measure, but something that we need.
But you can actually get the conductivity, right?
Yeah, from the Drude model we can
Optical,
get it.
yeah.
Yeah, optical. Yeah, we can get
you
that.
vary the temperature and
Oh, yeah, we have one measurement. We get the conductivity at 83 Kelvin from the free electron model and the 5 Kelvin. So you'll see increasing in reflectivity when you go from 4 Kelvin, 83 Kelvin to 5 Kelvin. So increasing in conductivity when you go in low in temperature. We do see that in optically. So this is addressing one of the things. So people can think, oh, what if this is a semiconductor? It's not really metal. But if you're semiconductor, we cool it down, the reflective will go up, right? So, but we see in the opposite, metallic behavior, the reflections goes up and the optical conductivity goes up.
in this particular measurement,
Yeah.
how many times have you repeated?
So in this particular one, this is only one example right here, but we have been coming to like 450 GPa many times. So we've seen OPEC and getting into a reflective this region many times, but the extra 30-40 GPa only happened once right here we're seeing. Only once. Yeah, that's something that we wanted to do, but we were consistently going into 450 GPa and seeing the black and shine. So around 450, this start to get reflective. Not the uniformly like a whole area, but some areas starting to get reflective. So we are seeing those small patches of getting into reflective hydrogen. So in a way that's confirming that we are seeing the exact same thing, but only one experiment we were able to push to another 30-40 GPa higher. Yeah, right.
Any other questions? If not, congratulations and thank you.
Thank
again.
you very much.
Yeah.
Yeah.